In this section, we're going to talk about electron configuration. Okay, so this is kind of a way of identifying an atom specifically by its electrons and what energy levels they're in, what orbital specifically they're in. So electron configuration notation eliminates the lines and arrows from the orbital notation. So you still have the number of electrons that are in each specific orbital. Okay? So the number of electrons is shown by a superscript, so it'll look like an exponent when you write it. And then you will basically write the name of the orbital, and then in the superscript, write the number of electrons that are in that orbital. So the electron configuration for helium, because helium only has a 1s orbital, but it has the 2 electrons in that 1s orbital, you would write its electron configuration as 1s2. Okay, 1s to the second basically, but it's pronounced or read as 1s2. So this means that there are 2 electrons in helium's 1s orbital, but that happens to be all of the electrons that helium has, so you don't have to go up to the next orbital. So the electron configuration describes the arrangement of electrons in the atom itself. So for an example, carbon, okay, so carbon has 6 total electrons, okay, its atomic number is 6, which means that it has 6 protons and 6 electrons. So your first 2 electrons can go into the 1s orbital, so you get 1s2. And then next up you have the 2s orbital, which again can fit 2, so you have 2s2. Now you only have 2 electrons left, so they go into the next orbital, 2p. So it's 1s2, 2s2, 2p2. So the integers in front of the orbitals, get a pen here, the integers in front of the orbitals here indicate the energy level of each occupied orbital. So they do have a very specific order that these orbitals will come in. The letters afterwards indicate the shape of the orbital, which you should already be familiar with these. It can be S, P, D, or F. And then the superscripts identify the number of electrons in each of these orbitals, okay, in each of the sublevels. All right. Now, again, remember, S can be up to 2. Okay, so it has to be, what is it doing? No, stop that. Okay, hold up, let me erase that. S can be, come on, maybe, all right. S can be less than or equal to 2. Okay, meaning that there is a max of 2 electrons that can go into each s orbital. P can be less than or equal to 6. Okay, D is less than or equal to 10, and F is less than or equal to 14. Okay, so if you have a completed energy level in each of these orbitals, you would have an S2, P6, D10, and F14. Okay, so those are just the max numbers for each one. Okay, so electrons will occupy the lower energy levels first, which means that they have that very specific order that they will go in. Okay, this is kind of showing based on energy level going up. It's a little funky to look at. The right side of this here, okay, where you can see 1s is obviously the lowest, 2s is next. But once you start getting up to 3p, you will notice that 4s actually has less energy than 3d. Okay, so you can see that you do 3s, 3p, and then 4s, and then you go back to 3d. Okay, and that trend continues when you add in the f's. Okay, because you've got 6s right here has less energy than 4f. Okay, so it gets a little bit confusing. We're going to go through it in a little bit better order, better view in a little bit here, but you can see the increasing energy on the left side here, and you can see the order that they go in. Okay, so each of these boxes that are shown over here can hold up to 2 electrons. Okay, so this is basically, if you were going to do orbital notation, you would have one arrow going up and one arrow going down in each of these boxes if they were full. Okay, so it's kind of the orbital notation idea, just looking at it this way. Okay, so now when we talk about how all of the orbitals get filled, we have the Aufbau principle, which we've already talked about, just didn't name it, but that is an electron occupies the lowest energy orbital that can receive it. Okay, so remember, each orbital has boxes that have like 2 seats in each box. Okay, s orbitals only have 1 box, p orbitals have 3, like we saw on this image, d orbitals have 5, and f orbitals have 7. So they can hold up to 2 electrons each. Okay, so you also have the Pauli exclusion principle. No 2 electrons in the same atom can have the same set of 4 quantum numbers. Okay, so this is what we went through in the last section. Okay, and that's why I kind of refer to it as basically the electron-specific like street address in a way. Okay, you have the country as the full atom, then you go down to state, which is your energy level, then you go down to city, which is the orbital type, and then you go down to street, which is the orientation of that orbital, and then you get your spin number, which is the specific house on that street. Okay, and there are only 2 houses on each street. Okay, so the Pauli exclusion principle basically is just stating simply no 2 electrons in one single atom can have the same set of 4 quantum numbers. Now, if you're comparing 2 different atoms, doesn't really matter if they have the same set of quantum numbers. Okay. All right, and now we also have Hund's rule. So Hund's rule is that orbitals of equal energy are each occupied by 1 electron before any orbital is occupied by a second. We also saw this in the last section when we were talking about our orbital notation. Come on. Okay, that's supposed to be an S. And then you have your 2s, and then you have your 2p. Okay, so if, say, we have, let's say, 7 electrons, okay, we've got 1, 2 go into 1s, 1, 2 go into 2s, and then we have 3 left over. Okay, so normally you would just think to do this. Okay, but that is incorrect because you have 3 different orbitals here in the 2p that all have the same energy. So this right here is basically overcrowding that specific orbital. Okay, simply because that electron right there that I just erased can actually move here and have more space. Okay, so electrons, when they can get it, they like their space. All right. Now, if we move up to 8 electrons instead of 7, that is where we would go in and put the electron in this orbital here, the second electron. Okay. So those are basically things that we've kind of already talked about, but now just going back and putting the name with them. Okay. So the electron configuration of boron is 1s2, 2s2, 2p1. So using only the electron configuration, how many electrons are present in an atom of boron? Okay, so we have 1s2, means that we have 2 electrons in the 1s, and then we have 2s2, which is 2 more electrons, and then 2p1, which is 1 more electron. Because remember, we are looking at basically the exponents here. Okay? So 2 plus 2 plus 1 means that boron has 5 electrons. Okay? What is the atomic number of boron, just using its electron configuration? Well, if it has 5 electrons, it needs to have 5 protons to balance that out. So the atomic number is the number of protons, meaning that boron has an atomic number of 5. And then write the orbital notation for boron. Okay, so we have 1s, 1s, 2s, and then 2p. Okay, so 1s has 2 electrons, so we've got up and down. 2s has 2 electrons as well, so it's up and down. And then 2p only has 1. So pardon my drawing over it, but there's your 1 in the 2p. Okay? So, number of electrons, 5. You just add up the superscripts, the exponents there. Atomic number, also 5. Okay? So the atom has a neutral charge, so protons equal the number of electrons. So 5 and 5. Orbital notation, we just did that. So we have our 1s orbital, our 2s orbital, and our 2p orbitals. And so you put 2 electrons in 1s, 2 electrons in 2s, and then you have 1 more electron that can go into 2p. So there you go. Okay? Alright, so this kind of helps you see it a little bit more as you're stepping up in energy. This only goes up to 4F though, but yeah. So this is kind of a way that you can see it. Is basically you write out all of your S's on the bottom here. Okay. So what you do is basically 1s, 2s, 3s, 4s, 5s, so on and so forth. And then you go back and above the 2 you write your 2p. Above the 3 it's 3p, and then 4p and 5p. Okay. And then D starts at 3, so 3d, 4d, 5d. And your F starts at 4, so 4F and 5F. Okay? And then you just start drawing lines like this that go diagonally from the top all the way through. Okay? And then you write them out in the order that you contacted them. Okay? So you have a 1s, then you have a 2s, then you go 2p, 3s, and we're using this one here. We have a 3p, 4s, then we're up here, 3d, 4p, and then you go to 5s. Next one here, you have 4d, so 4, and then 5p, and then we would go to 6s, I just didn't have it written up there, and then you go up to this one, and that, hold on, something's, yeah, no, that's right, okay. Then it's 4F, 5D, 6P, okay? And then you continue going on like that. So if you write out the whole thing, you can see how they did the diagonals this way, okay? And there you go. So that's how you tell which one comes next, which orbital comes next. Okay? So this is another way of kind of writing that out. They just wrote it kind of the other way. So again, you just write out your 1s to 7s in your first column here. And then starting with the second row, you start out your p's, or you write out your p's, 2p to 7p, and then starting with the third row, you write out your 3d to 6d this time, and then starting with the fourth row, you write out 4f and 5f, okay, making sure that it all lines up. And then you just start with the diagonals, go through 1s, 2s, then 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, no, that's not what I wanted. Here we go. 4f, 5d, 6p, 7s, 5f, 6d, 7p. Okay? And that's where it ends. Okay? Now, they didn't list all